that puts a
Bloom is a senior studying mathematics and finance, interested in applying mathematical and data-driven methods to problems across disciplines. His research projects during his time at SMU have included modeling nonlinear light beam propagation, exploring historical detriments of SMU student success, predicting ice fog events in Alaska, and modeling the spread of COVID-19 in Texas. This past summer, he participated in Dartmouth's Computational and Applied Mathematics Research Program in partnership with the U.S. Army Corps of Engineers Cold Science Research and Engineering Laboratory. Jonathan Lindblom is also in the Alternative Assets Finance Honors Program, as well as a trumpeter in the Mustang Band. After graduation, he plans to pursue a research career in a quantitative field. Take it away, Jonathan.
Thank you, Beryl. You can all see the full screen, correct? Okay, cool. So the research I'll be presenting today is the research I did this summer at the Dartmouth program about ice fog. The program specifically focused on inverse problems, computational methods, and the environment. So it's a heavily mathematical and computational program. I learned a lot of neat techniques that I'm going to show you about today. So the team I worked with this summer was myself and a couple other undergrads. Evan Lipton is from Yale. Shaylee Manenhart is from Southern Mississippi University, so another SMU. And then Ivy Yan is from Dartmouth. And so fun fact about Ivy Yan is that she actually lived in Shanghai all summer. So we had quite an interesting time working on this project with her as well. So what is ice fog, right? Ice fog is basically treated as fog, except it's a lot harder to predict. And it, in some cases, is more deadly. And by deadly, I mean like road hazards, plane hazards, basically just visibility patterns, right? It usually happens in very cold regions, such as like Fairbanks, Alaska, so very up north. And it usually happens right around like negative 38 degrees Celsius. And so for our, we'll get into this, but for the data that we have, we don't actually have data of when ice fog occurred, only the temperature data, because no one actually collects data as to when ice fog occurs. So the best thing that we could do in trying to predict ice fog, which is what we tried to do in our research, was to just say a cutoff. So if the temperature is below negative 38 degrees Celsius, we just call it ice fog, even if there's not actual ice fog, right? So this is an example of like the visibility conditions, right? So you probably don't want to be driving out on the road during this, right? So the data that we had, we have a big grid forecast, which I'll show you in a second. That's the GFS, the Global Forecasting Systems, weather predictions for the latitude-longitude grid in this region that we were studying. In companionship with that, we also have the actual observed temperature data at these several weather stations. So for the work that we did over the summer, we looked at 3 stations specifically. But this semester, I'm actually continuing on as an intern and working up, kind of developing the project more fully fledged, right? So in the station codes for these weather stations, if you're so curious, are PAEI, PAFA, and PAFB. So you can find all this data online if you go look through like NOAA weather sources. And all of this research was in partnership with the Cold Regions Research and Engineering Laboratory. People just call it CREL. So we got to talk with some of the researchers there, and they helped us through it. So this is an example of the forecasting data that we have. This is the grid, right? And so these little X's on here are all the stations at which we have the actual observed temperatures that were observed at the corresponding prediction times. To give you like an idea, kind of the problem is that we don't make these weather predictions on very small scales. We make them for the entirety of the Earth's surface. And so when you look at the predictions, you're making predictions over massive grids that aren't very accurate at very fine scales. And so the purpose of kind of the research we were doing is saying, okay, you only get the predictions over a very large region. Now, how can you maybe incorporate local idiosyncratic data that alters the predictions on a larger grid to be more accurate locally? So here's an example of what I'm talking about. So the dark blue line is an example of a time series plot of the observed temperature value. And all these other lines are the predicted values at several other intervals ahead of the time, right? So for the 0 hour, the 12 hour, 24, 48, 72 hours in advance of the time. And so you'll note that like as you get closer to the actual time, so time 0, the predicted value kind of makes its way down closer to it, but it's still pretty off, right? So that's just kind of a twofold error, is that as you further away in time, you're worse at predicting. but also even your time zero, according to the model, is still itself wrong. So basically what we tried to do is say, okay, we want to model the function that takes us from the predicted values that we're getting from the GFS data and match it up with the observed values we get at the actual weather stations. And so to do this, you might do like a linear approach. And so we did the linear approach not because we thought it would be accurate, just to get like a baseline comparison against it, right? And so, this is just your standard linear regression. It's actually the Bayesian flavor of it, so it's a little bit more sophisticated. But the idea is that, basic math, right? Y equals mx plus b. We're going to estimate what y is. We're going to estimate what b is. And so then predict the observed temperature value that we actually see based off of, y equals mx plus b. And so this is kind of how it looks. And so you can actually apply this back to that time series we just looked at and get a region that you would expect to see almost all of your values, right? And so one thing you can note is that around this region, it's constant along the entire span of the predictions, because the variance that you're allowing in this model with the Bayesian linear regression model, it's constant for all temperature values. And so we actually had a priori knowledge that likely there's a higher variance when it gets very cold. So when it gets very cold, we thought in advance that our predictions would be much worse than when they're in normal temperature spans. So here's an example of kind of like the linear regression approach. What I'm talking about with the time horizons. As you get closer and closer, so march your way from 72 hours ahead all the way to 0 hours, the variance that you're going to estimate when you do this regression process will decrease, which is what you expected, right? Because as you're getting closer to the time, even though the linear predictor is bad, you think it will be less worse than the longer time horizons. So like the main thing I want to get across here is that using the linear model, what it tries to do is it casts a wide net in terms of the probabilities, like we were looking at on the previous slide. With this, imagine the blue shaded region as like the interval that you think you'd see like almost all of your values. You can imagine with this linear model, it's casting a very wide net. It's saying, okay, I'm just going to fix it as big as I can, and then hopefully everything fits in there. But kind of the approach that we did in our research that was kind of novel was that, okay, we don't want to do that. We don't want to model all of the errors along the regression line as just being normally distributed. We actually want to let that distribution itself vary along the along with the predicted temperature value. So for example, we want there to be a higher variance down in like the 230 range as opposed to the 270 range and this is in kelvins, sorry. Cool. So the way we do this is we exploit the formula. It's a formula for probability theory. This is just the change of variable formula. But people, very smart people, much more clever than me, than I will ever hope to be, they developed very complicated methods that use machine learning or use polynomial chaos expansions that allow you to very cleverly estimate the function that will take you to allow you to achieve basically what I just described doing, correct? So here's an example of like some of the results that we had in our research. This is when we were applying the neural network approach. So this is what's called a real non-volume preserving flow, which is a mouthful. But to give you an idea, rather than assuming just normal distributed noise, we actually want to let our noise look like this. So if you imagine like conditioning on the distribution in the 72-hour predicted temperature dimension, so vertically, what we're basically saying is higher up at the top, we want there to be a smaller variance in this direction. So it's thinner up here than it is further down in the tails. So that's basically our research in a gist, was figuring out how do we estimate this function that will take us there. And so this was the result that we saw from the neural network approach. And this is what's called a probability density. So just imagine this as being almost like a heat plot as to where you would expect to see your values distributed along that linear regression line that I showed earlier. So it gets very fat at the bottom and it's very thin at the top, which is kind of what we wanted. So here's another example of how the density changes as you use the approach that we use. And so it's taking you from that very, this is called a Gaussian distribution. It's taking from there and making it into this very just non-standard distribution. There aren't parameters that you can estimate like an alpha and a beta from just normal statistics. So here's an example of, you can then draw observations from that distribution. And this is a comparison where the blue are the actual data points that we have, and then the red are the artificial data points that we generate using our model. And so you can see that it probably fits like pretty well. And there's a lot of tests that I won't go into that you can check to see that, yes, it actually does fit very well. And so here's the difference in the density that we see when we use the polynomial chaos approach. So it's similar, but it also is different in its shape. So you can, after you go and do this, you can then after the fact make the same kind of lines that we drew earlier, and you can see the same nets that we're putting on our predictions. But you can note, like I mentioned before, that the linear approach, which would be the blue, that puts a fixed width around your prediction of where you think the actual temperature value will be. Whereas these other approaches, they allow the green bands and the purple bands, they allow it to vary along the curve based off of what the predicted temperature was at the time. So that was really the power in the approach. And so you can then translate all this over into saying, okay, what is the probability that the temperature in time is less than negative 38 degrees Celsius? And so what you'll see is that the linear approach will always give you a really high estimate as to what you think the probability is for ice fog. Whereas these other approaches, they are much more conservative or hopefully more accurate. And so part of the research I'm doing this semester is saying, okay, how do we tell which is the most accurate, right? Because I can show you plots for 3 different models that say, here's the probabilities of ice fog, but how do you know which one is the best? And so to do this, you use things called scoring rules that are like a scorecard for your predictions. And hopefully, like my end goal by the end of the semester is to translate this into spatial data as well, so that you can, kind of like what the temperature plot I showed you earlier, this would be the same post-processed plot, except instead of representing temperature, it's representing the probability, right? So the more red it is the higher probability of ice fog being at that point, whereas the deeper purple is probably very low probability. So special thanks to Dr. Parno and Dr. Gelb. They were our 2 advisors from this summer for the project. Dr. Peckham was a researcher at the lab that helped us out quite a bit. And Casey Dowdle was another worker at the lab who kind of developed the whole package that we used for the neural network approach for our research. So shout out to him because he was very helpful.
All right, thank you so much, Jonathan. If anybody has any questions for Jonathan, please go ahead and throw them in the chat. I'd also like to thank Jonathan because this little mini symposium was actually his idea. So he's the mastermind behind this, of getting all of us together so that we can learn more.